So given input variables x, say x sub 1, x sub 2, until x sub d, we want to learn how it affects variable or output y. Okay, so this mapping relationship between the input variables and y, output y, may be expressed in this statement: y is equal to f of x plus the error term. So the f is an unknown function of the x, okay? And in statistical learning, we will learn how to estimate this function f, okay? So there are two reasons on why we want to estimate f. First is we want to be able to predict a certain response na y from this features x, okay? And this is what we term as predictive na modeling. There are also cases wherein we don't want to predict. Rather, we want to understand the relationship between our features and a certain response. Okay, and that is inference. Now let us discuss one by one. So in predictive modeling, there are some cases wherein a set of input x are readily available, but the y is not easily obtained. So in this setting, it may be represented using this statement: y hat is equal to f hat of x, wherein y hat is the prediction for y. Okay, and the f hat, on the other hand, is the estimate for the function f. Okay. So in this setting, the f hat is considered as a black box, in a sense that one is not typically concerned with the exact form of f hat, provided that it yields accurate prediction for y. Suppose we have this example. We have the advertising budget for TV, radio, and newspaper, and we can predict the sales. Okay, so our concern is to be able to predict the sales given the budget for these three media. Okay, so we are not concerned whether the TV is more effective than radio or newspaper, or whether newspaper helps at all, or whether people listen to radio and it helps with the sales. We are just concerned with the prediction of sales. Okay, so that's what I meant when I said that we are not concerned with the exact form of the estimate f hat, but as long as it provides an accurate prediction of y. Now, since this is just an estimate from the word itself, that means that there will be inaccuracies and there will have an error. Okay. Now, these errors may be used to measure the accuracy of y hat. So, for instance, we have this plot. The red dots represent the data points. Okay. So, given x or given input x, what is the output y or the observation y? Okay, suppose this is y hat is a prediction that is done by the model. So the distance in between the output y and the prediction y hat is what we term as the error or the residual. So this error may be used to measure the accuracy of y hat. So the closer the observation y to the prediction y, then that means that the error is lesser, then the more accurate the model is. Okay. Now let's proceed to the inference. Now, we are often interested also in understanding the way y is being affected by the changes in x. Okay? Now, how does y change as a function of our variables? X sub 1, x sub 2, until x sub d. Okay. Now, in this situation, we wish to estimate the F, so which is the F hat, but our goal is not necessarily to make predictions for Y. Rather, we want to understand the relationship between X and Y. Okay. Now the F hat cannot be treated as a black box. Why? We want to know its exact form. We want to know how the we want to know how the estimate is done. Okay. So we could answer the following questions. So pose given this plot, right? So given the same example, we have the sales, given the budget for TV and radio and newspaper. So the sales are expressed in a function of TV, radio, and newspaper na budget. So we want to answer such questions like, which predictors are associated with the response? So there are some cases wherein only a few na predictors are substantially associated with Y. So for instance, let's say, what if we don't need the newspaper? TV and radio are substantially enough to predict the sales, okay? Or in other words, we could identify only the few na predictors among a large na set of possible na variables. And what is the relationship between the response and each predictor? So for instance, we wanted to predict the sales, and we can see here that the relationship of TV and sales, the relationship of the radio and sales, and newspaper and sales. So we can see that we can see a substantial increase in sales as the TV budget is increasing. Okay, we can also see here the difference that the increase in sales is much slower as we increase the budget in the newspaper. Okay, so there are some predictors wherein they have a positive relationship with the sales, and while others have opposite relationship. So yeah, and another question that we could answer is, can the relationship between Y and each predictor be adequately summarized using a linear equation, or is the relationship more complicated? So for instance, is it safe to assume that the relationship of TV and sales is linear? Can we say the same for radio and newspaper? Okay. So in reality, or in the simplest na form, it is easy to say that relationship of two variables is linear. However, in the real world setting, there are some cases wherein the relationship might be more complicated and cannot be captured by a linear na model. Okay, so given this problem or advertising na data, so we could answer questions like, which contribute to sales more? Is it TV, radio, or newspaper? And which media generate the biggest boost in sales? And how much increase in sales if we invest more on TV? Okay. So this kind of problems will fall under the inference na paradigm.